So today we have Cedric with us. Cedric was a master's student here in Waterloo with Laura Sanita. And after that, like he was also a research assistant with her for a year after his master's before he went to LSE for his PhD with Lachi. Today is going to talk about strongly polynomial time label correcting algorithm for linear systems with two variables per inequality. So Cedric, you can start whenever. Yeah.
Okay. First, thanks for the invitation. Today I'll be talking about recent work that I've done with my advisor Latsi and Bento. Right. So to put things into context, we'll be looking at linear programming. So I believe this audience needs no introduction to LP, but nevertheless, I'll still state the standard form of primal and dual LPs. We have AX equals to BX non-negative, and the dual, which I want you to pay more attention to, is maximize B transpose Y subject to A transpose Y less than or equal to C. And today we'll be looking very closely at the dual linear program. In particular, we want to devise strongly polynomial algorithms to solve the feasibility of the dual LP. So as we all know, currently known LP algorithms such as the ellipsoid method and interior point methods are weakly polynomial, meaning that the runtime depends on the size of the numbers occurring in the input. And in contrast, a strongly polynomial algorithm does not depend on, its runtime does not depend on the size of the numbers. So in particular, the first requirement is that it should only perform poly-NM elementary operations, where n is the number of constraints and m is the number of variables in the primal LP. And an additional requirement that we need is that the numbers that occur throughout the computation should remain polynomially bounded in the input size. And an important problem that was raised by Stephen Smale is whether there exists a strongly polynomial algorithm for LP. By the way, if you guys have any questions, feel free to stop me at any point in time. So today we'll be looking at the dual feasibility problem. Either you find a solution to A transpose Y less than or equal to C, or you conclude that it's infeasible. So if we do not put any restrictions on the constraint matrix, then this is equivalent to solving the original problem that we've stated in the first slide just by strong duality. So what we'll do is we'll look at the special case when every column of A has at most 2 non-zero entries. Then if you look at the dual, the system, every inequality has 2 variables. And so we will call such systems a 2 variable per inequality system, or 2VPI in short. And to simplify the problem further, without loss of generality, we can assume that every inequality is monotone. What I mean by monotone is that the coefficients that appear in the 2 variables have opposite sign. And the reason is because if it's not the case, then you can perform the following reduction. For each variable yu, you introduce 2 new variables, yu plus and yu minus. And then you replace each inequality with the following, with 2 inequalities, depending on whether their signs agree or disagree. And then I argue that this reduction is without loss of generality, meaning that you can always construct a feasible solution to the original system from the new system. And this is easy to see because if you have a feasible y to the original system, then if you define y plus by y and y minus by minus y, then clearly it satisfies the constraints of the new system. And conversely, if you have a feasible solution to the new system, then you can define y as the average of the two. And then it's not hard to convince yourself that this is a feasible solution to the old system. So now that we have our 2VPI system in monotone form, we can scale each inequality to ensure that every inequality is of the form yu minus gamma EYV is at most CE, where the gamma E is positive. Then the benefit of doing this is now we can represent the monotone 2VPI system as a directed multigraph on n nodes and m arcs. So each inequality corresponds to an edge, and each variable corresponds to a node. And each arc has an arc cost of CE and gain factor of gamma E. So throughout this talk, I will be using this tuple to define the cost and gain factor of any arc. A nice property about monotone 2VPI systems is that if the system is feasible and is bounded in the positive side, then it has a unique pointwise maximal solution. And the proof is to just take two feasible solutions of your system and define a new vector, which is just the pointwise maximal of the coordinates of y and y prime. And then it's also not hard to see that z will also be a feasible solution to your system. So by repeating this operation, you will get to the pointwise maximal solution ultimately. So let us go through some basics of 2VPI systems. Now we'll reason 2VPI systems in terms of its directed multigraph representation. So for a walk in G, we define its cost and gain factors as follows. The gain factor, which we call gamma P, is just the product of the gammas in your walk. And the cost of the walk is just the discounted cost of the walk. So let us go through an example to make this concept clear. Suppose we have this system which consists of just three inequalities. Then the directed multigraph representation is just a path. And now if we take P to be this entire path, then C of P is just -1 plus 1 times 1 plus 1 times 0.5 times the cost of the third edge, which is 2. So this is just 1. And then the gammas are just the product of 1, 0.5, and 2, which is 1. Okay. Now, the reason why these two concepts of cost and gain factors are important is because they allow us to induce valid inequalities of our system. So specifically, if you take a UV walk P, then you can get a valid inequality of the form YU is at most CP plus gamma P YV. And the way to see this is if you just look at this simple example again, if you take the first inequality plus 1 times the second inequality plus 0.5 times the third inequality, then what you get in the end is just the implied bound. Okay, so we will be in particular interested in this bound when U is equal to V. So instead of a walk, now we have a closed walk. And in this case, we can deduce information about the variables. In particular, if the gain factor of the path is less than 1, then by rearranging the implied bound, implied inequality, we get an upper bound on yu. Similarly, if the gain factor of the walk is greater than 1, then we get a lower bound on the variable. And if the gain factor is equal to 1, then we don't learn any bound on variables, but we get like an inequality that doesn't involve any variable. So if C of P is non-negative, this is just a tautology. But if C of P is negative, then this gives us an infeasibility certificate for our system. So it is helpful to think back to the shortest path problem. This is when you have a negative cost cycle in the graph. We'll need a few more concepts. So a directed cycle, if we look at the directed cycle C, we say that it's a unit gain cycle if its gain factor is exactly 1, flow absorbing if it's less than 1, and flow generating otherwise. And a bicycle consists of a flow generating cycle, a flow absorbing cycle, and a path connecting the two. So here's an example of a bicycle. Here we have C, P, D. And we will say that the unit gain cycle C is negative if its cost is less than 0. Now, I haven't defined what the cost of a cycle is. I've only defined what the cost of a walk is. But you can think of a cycle as a walk by anchoring the starting point at any node in the cycle. So if you do this, then the cost of the cycle is well defined for a particular anchor point. And if the cost of, let's say, C of u, where Cu is the cycle anchored at u, is less than 0, then if you anchor the cycle at any other node, you can still show that the cost of the walk is negative. So this is well defined. Similarly, we will say that a bicycle is negative if the following inequality is true. Now, what this inequality is trying to say is that if you look at the flow absorbing cycle D, you get this upper bound on YV. So let's say the path goes from U to V. This term represents an upper bound on YV. And then this upper bound is propagated along the path to yield an upper bound on YU. So this whole thing is an upper bound on YU. Now, if you look at the flow absorbing cycle at the other end of the bicycle, we know that it gives us a lower bound on YU. So this inequality tells us that the lower bound is higher than the upper bound, which means that our system is infeasible. So this, I believe the bicycle in this example is negative. So C of D, 1 minus gamma D, this is just, I believe this is 2. And then gamma P here is 0.5, CP here is 0, and the lower bound implied on YU is 2. So 2 is greater than 1. Now, these two structures are crucial for our problem because they completely characterize the feasibility of our system. And this was shown in Shostak back in '81. He showed that the monotone 2VPI system is infeasible if and only if its directed multigraph representation contains a negative unit gain cycle or negative bicycle. So through this glimpse into considering close walks, we know that close walks will play an important role in the problem. So we are interested in computing the best bound that can be obtained around a closed walk, or more specifically around a loop. So we'll define a loop as a closed walk whose endpoint does not occur as an intermediate vertex. And then for every vertex, we use this notation to define the set of loops starting and ending at U of length at most n. Then we're interested in computing the following two quantities, YU high and YU low. YU high in words means that it represents the best upper bound that you can get for the variable YU around a flow absorbing loop. And YU low, on the other hand, is the best lower bound that you can get on the variable around a flow generating loop. A key observation that we'll make here is that if we try to guess YU high, for example, and if we propagate the guess around the loop, we can learn something about the bound implied by the loop. What I mean is, let's just look at this example. This is a flow absorbing loop, and the bound implied by the loop is YU at most 2. So for example, if your guess is higher than the implied bound, let's say 3, then by propagating it to V and back to U, so you will get 2.5 by propagating it, just using this inequality. And then now if you send it back, you will get 2.5. And if you keep repeating this operation, you will converge to the true bound implied by the loop. On the other hand, if you guess something that is lower, say, for example, 1, then by propagating to V, you get 1.5, and you get something that is higher than your initial guess. So this operation will play a crucial role in the algorithm, because we will be propagating guesses in the graph to determine the loop, to determine YU high and YU low.
What do you mean by propagating a guess?
Propagating means just, yeah, so here's what I'm going to explain the propagating operation in more detail in this slide. So propagating can be thought of as a Bellman-Ford operation. So Bellman-Ford, you start with, for the shortest path problem, single source shortest path problem, you start with 0 at the source node and infinity everywhere else. And then you propagate 0 into the graph, and what you get in the end are shortest path distances. So this is akin to that, except now we have gain factor on the arcs. So suppose we have an initial guess delta on YU high. Then we initialize YU with our guess and infinity on the other vertices. And then we repeat step 2 n-1 times. This is just taking either the min of YV or, yeah, this is just a Bellman-Ford step, essentially. And the crucial thing to note here is that we only perform this update for nodes that are not U. And then at the last step, we update the bound, we update the label at U. So this is like a label correcting algorithm, because it continuously lowers the labels on your vertices. Right. So let P star be the loop that gave YU its value after running the grapevine algorithm. Then it is not hard to see that YU is exactly equal to the minimum of this quantity, just from the updating operation. And then we can, by examining the relationship between YU and our initial guess delta, we can learn whether our guess was too high or too low. So if the return YU is less than delta, then we know that our guess was too high. And this is evidenced by P star. On the other hand, if YU is at least delta, then we know that our guess was too low. So we can sort of use this in a binary search framework to zero in on the correct value of YU high. Give a brief history of the algorithmic developments of this problem. The first algorithm was given by Nelson. He modified the Fourier-Motzkin algorithm to get a quasi-polynomial runtime. And then afterwards, Shostak in 81 characterized feasibility in terms of cycles and bicycles in the graph, as we have just seen. The first weakly polynomial algorithm for the problem was given by Ashbal and Shiloak. And this is essentially the binary search framework that we just saw. And then subsequently, Megiddo changed the binary search framework into a parametric search framework, which allows him to convert the algorithm into a strongly polynomial algorithm. And then eventually, Cohen and Megiddo developed faster algorithms for the problem. And the current record holder is held by Hochbaum and Nau. It is also a Fourier-Motzkin algorithm, but has some binary search framework. It's a combination of Fourier-Motzkin and binary search. And the running time is mn square log m. So all the algorithms that I've just mentioned, other than the non-polynomial ones, they operate on a similar principle. So what they do is, for each variable, they maintain an interval of possible values that a variable can have, and then they progressively shrink the interval either using binary search or parametric search. In Ashba and Chilliwack, they maintain an interval of possible values for yu high, and then they slowly shrink the interval. But in its core, the idea is the same. And once you find a feasible value for a variable, then you just fix it and repeat it. Now, when you fix a variable to a value, you've obtained another 2 VPI system with one less variable. So you can then solve your problem. Now, if you look at these search techniques, which are based on binary search and parametric search, they are quite different compared to combinatorial optimization problems described by constraint matrix A. So described by, these are matrices with at most 2 non-zero entries in the column. So these are the combat problems that we know and love, such as max flow, shortest path, min cost flow, and so on. Most strongly polynomial algorithms for these problems, in fact, they operate using one of the following 2 principles. Either you maintain a feasible solution at all times, and you slowly improve your solution until you get an optimal one. The other paradigm is you maintain a super optimal solution, which is not feasible, and then you slowly move towards feasibility. So an important class of algorithms in this second class are so-called label correcting algorithms. So label correcting is best illustrated on the shortest path problem. So given a directed graph with arc cost C, we have a target node T, we want to find the shortest path tree to T. Now this problem is actually a special case of monotone 2 VPI systems because they can be formulated using these constraints. And what Bellman-Ford does is you start with very high values of Y, and then you slowly run the propagating step to eventually converge to the shortest path label. And these shortest path labels turn out to be the pointwise maximal solution of this monotone 2 VPI system. So, right, so here's exactly what I mean. When you run the label correcting algorithm, if you have a constraint that is violated, then you pick it and you set it to equality, and you keep repeating this. Now, what Bellman and Ford shows is that this algorithm terminates in n iterations if there's no negative cost cycle in the graph. In fact, it's if and only if. So a natural question is to ask whether this label correcting framework can be extended to general 2 VPI systems. Meaning that we now have gain factors on the arcs. As we have seen in the previous example, this method doesn't even converge, right? Like if we look at this example, by propagating the labels around the flow absorbing cycle, this method doesn't even terminate finitely. So we need to do something better here. So before going into detail about our algorithm, I will introduce you another class of combat problems that can be described by monotone 2 VPI systems. It's a special case of Markov decision processes. So the input here is a directed multigraph with arc cost and gain factors. Actually, I should call them discount factors because now they're restricted to be between 0 and 1. And the goal now is to select an outgoing arc from every node so as to minimize the total discounted cost over an infinite time horizon. Right. So this problem is very similar to shortest path. The formulation is slightly different because now we include a gain factor for every arc. But what we're gunning for is essentially the same thing, which is the pointwise maximal solution. So one could imagine a label correcting framework where you start with very high y values again and slowly correct the violated arcs. So this is, in fact, value iteration, which is a pretty popular algorithm to solve Markov decision processes. And it has recently been shown to be not strongly polynomial by Feinberg and Huang, even for the special case of deterministic Markov decision processes. Right. So now I'm going to take a segue here and tell you about a new topic. But after this, you'll see how these two, the concept of label correcting and fractional combinatorial optimization will combine together. So, okay, now let's put label correcting aside and consider the following problem. We have a finite set of elements and a set of structures called X. These are 0, 1 vectors. So you can think of, for example, cycles or paths. And then the set E will just be the edges in your graph. Now, the problem is as follows. You're given two functions, f and g, where g is positive. And now you're asked to find the structure that minimizes this ratio. This is a very general framework and encapsulates a lot of problems. But even if we restrict f and g to be linear, it also captures a lot of very important problems in COMBOP, such as the minimum cost to time ratio cycle and the minimum ratio spanning tree problem. So here, the cost would be f and the time would be g. And then the chi would be the set of all cycles in G. Okay. Now, when f and g are linear, it has been shown by Megiddo that we can solve this in strongly polynomial time, assuming we have a strongly polynomial algorithm for the non-fractional problem. So the non-fractional just means that the same problem except with linear objective function. So for example, the minimum ratio spanning tree, the non-fractional problem is just the minimum spanning tree problem. In fact, this was the main motivation behind the development of the parametric search technique. And the main idea of parametric search is that it simulates the algorithm for the non-fractional problem with an indeterminate parameter delta. So now the costs are all parametric functions in terms of delta. And now you run the non-fractional algorithm as if delta is part of your input, but is an unknown quantity. Yes. And then, I think I shouldn't go too much into details of parametric search, but that's generally the main idea. Now, for those of you who are less symbolic inclined and prefer a more iterative approach to this problem, we can also solve it using the Newton's method. So here's how we do it. First, we reformulate the problem as this optimization problem. And we're trying to solve for delta star. Now, if we rearrange the constraints, then we get this function here. And we are particularly interested in finding the structure that maximizes this function. So we want to find the structure that most violates the inequality of our optimization problem. So we will denote this parametric problem as h of delta. Now, a few preliminary observations. The function h, it is convex because it is the upper envelope of linear functions. It is increasing because g is always positive, and it is piecewise linear. So the function h is very nice. It also tells us that it has because of these three properties, the function h has a unique root. And our goal now can be recasted as finding the root of this function h. So if we have an algorithm to solve the parametric problem h of delta for any delta, then we can sort of determine at which side of the root are we. In particular, if h of delta is positive, then we know that we are to the right of the root, negative otherwise, and 0 if we are at the root. So the picture is something like this, and delta star is what we are computing for. So this suggests to use root finding techniques such as the Newton's method to solve fractional combinatorial optimization problems. Right. So here's Newton's method for this problem. We pick an initial starting point, and then we solve the parametric problem. And then while h of delta is non-zero, then we take the negative gradient direction until it hits the x-axis. So in this case, let's say we're at delta I, and then we solve for, and then this is h of delta I. Then we take the gradient direction to get delta I plus 1, and we repeat the procedure until we converge to 0. In the case of linear fractional combinatorial optimization problems, Radzik proved that this method terminates in a strongly polynomial number of iterations. Right, so that's a bit about fractional combop. Back to 2VPI, we'll now try to combine these two problems. Recall, we are interested in computing yu high, which is just the best upper bound given by a flow absorbing loop. This is actually a nonlinear fractional combinatorial optimization problem in disguise, because every loop can be represented as a 0, 1 vector, and then the numerator is just the cost of the loop, and the denominator is just 1 minus the gain factor of the loop. So it is not as it is a non-linear, it is not a linear problem, but still it falls under this framework. Now the associated parametric problem is just the same. We're interested in solving for, so this is just minus f of x plus delta g of x. We're trying to find a structure that maximizes it. So good news for us is that the grapevine algorithm can be used to solve the parametric problem. So we're in good shape. I included an asterisk here because the grapevine algorithm doesn't quite solve this problem, because we have this extra restriction that the loop return should be flow absorbing. But nevertheless, we can handle this technicality. So with this in mind, we can now try to solve for yu high using the Newton method. So first we pick an initial delta, and then we solve the corresponding parametric problem for that delta value. As long as h of delta is non-zero, we take the Newton step. This is just f of x over g of x. And then we solve again and we repeat the procedure until we converge. Now the question is, how many iterations does this method take? As early as 2002, Madani has looked into this problem, and he gave a weakly polynomial bound on the number of iterations. So here are some of our main results. We were able to strengthen Madani's analysis by showing that the Newton's method in fact computes yu high in a strongly polynomial number of iterations. And this is achieved using two main ingredients. The first is that we identify a so-called gauge symmetry of the Newton's method. So the term gauge symmetry comes from physics, and I have to admit I don't understand the physical interpretation of that. But in the algorithmic world, what it means is that there is a class. So let's say you're given an input instance and you run Newton's method on it. There is a way of modifying the data of your problem such that Newton's method behaves the same. So what this gives us is the power of not performing the analysis on the input instance. We can actually modify the data of our instance without modifying the behavior of Newton's method. And this will be particularly useful when we show the strongly polynomial bound. And then the next ingredient is that using this gauge symmetry insight, we were able to accelerate the Newton-Dinkelbach method. And then this acceleration also allows us to improve some bounds that were previously proved for linear fractional combinatorial optimization problems. So Radzik in '92 was the first to give a bound. He improved it to e squared log square e. And then recently in '06, this bound was brought down to e squared log e. All these bounds hold for the classical Newton method. And with the acceleration technique, we were able to bring this down further to e log e iterations. And then the final product of this is a label correcting algorithm for the 2VPI problem, which runs in mn iterations. So now I'll talk about the crucial component of our analysis, which is the gauge symmetry. So for this, let us move back into the fractional comb-up world, where an instance is defined by two functions and a set of structures. And pick lambda to be some value. Now, instead of using the original cost function, let us use the modified cost function, f lambda, defined as follows. Now, the good thing about modifying the cost function this way is that no matter which lambda value you pick, Newton's method exhibits a similar behavior on both instances. So if you run Newton's method in the original instance, initialized with delta naught, then the behavior is exactly the same if you run it on the new instance, initialized with delta naught minus lambda. And the proof is really simple, which is why I included it in the slides. So if you expand out the definition of the parametric problem for the new instance, then what you get is essentially the parametric problem for the original instance, but shifted by lambda. So you can think of it as let's say if this is the h function for the original instance, let's say this is delta star, and suppose I initialize here, then what gauge symmetry says is now I define a new instance by shifting the h function. So now my delta star is here. And so to obtain a similar behavior of Newton's method, I also shift my delta naught from here to here. So because the curvature of the function is the same, we will obtain similar behavior on both instances. Geometrically, that's the idea. Right. So what can we do about, how can we use this insight to accelerate the Newton's method? For analyzing the Newton's method, it is helpful to divide iterations into two types based on whether the gradient drops by a lot or not. So we fix a constant between 0.5 and 1, and we say that the iteration is good if the gradient drops by at least a factor of alpha. Otherwise, it is bad. The reason we segregate iterations this way is because good iterations are easy to analyze, and there are not too many of them. So the bottleneck are really the bad iteration. Now, suppose we look at a sequence of bad iterations. What we know is that the iterates, they shrink geometrically. The distance between the iterates shrink at geometrically. So, for example, on this axis, the orange dots are the good iterations and the red dots are the bad iterations. And if you have a consecutive sequence of bad iterations, then the gap between the iterates shrink by a geometric factor. So a natural thing to do is that whenever we encounter a bad iteration, let's say from delta 1 to delta 2, instead of continuing with Newton's method, we try to jump ahead of the sequence of bad iterations. Now, if this jump is successful, meaning that we are still to the right of delta star, then we have made substantial progress. So we continue, as long as we have good iterations. Let's say we get a bad iteration again, then we would try to avoid the long sequence of bad iterations in front of us by jumping ahead. And let's say, for example, here we overjumped. Then what we do now is we say, okay, jumping ahead doesn't work, so we'll just follow the conventional Newton iterates. So this is essentially the idea of looking ahead. And this is the amount by which we jump. And this is really just the sum of the geometric series whose factor is given by this. Right. So why does this accelerate Newton's method? Because we have gauge symmetry. Remember, because of gauge symmetry, we can assume that the optimal value that we are aiming for is 0 without loss of generality by just shifting the h function horizontally. So with this extra assumption plus acceleration, we can show that the cost of each structure decreases at the geometric factor. And this is very helpful in arguing convergence. So let us see how acceleration allows us to speed up Newton's method for the linear case. Again, we have a set of m elements and a set of structures. So now instead of f and g, we now have vectors c and w. C is the cost and w are the weights. And now we're trying to find a structure that minimizes this ratio. Now here's a proof of theorem 2, which I've shown you before. Let x1 up to xk be the structures produced by the look-ahead Newton's method. Again, by gauge symmetry, we can assume that the optimal value is 0. And then we know that the cost of each structure decreases geometrically. Now, if we apply the following lemma found in Radzik's survey, but it was actually credited to Gummans, which states the following. If you have a sequence of sums which decreases by a factor of 2, and these sums are positive, then your sequence cannot be too long. In particular, the maximum length of the sequence is m log m, where m is the number of elements. This bound is actually tight. You can actually construct instances which satisfy this condition with the same asymptotic length. Okay. So now let us apply the same idea to 2VPI. So how does gauge symmetry look like in 2VPI? In the linear fractional combat world, we modify the function f by f lambda. And this is f of x minus lambda g of x. In the 2VPI world, we will be modifying the edge cost by the usual modified cost seen in many network flow algorithms. So this is this is the reduced cost So for a given set of node potentials, P pi of uv is just the reduced cost on that edge. And then with this transformation, you can show that the cost of every loop is given by the original cost minus pi u times this thing. So recall that the cost of a loop is f of x in the fractional combinatorial language, and 1 minus gamma is g of x, and this pi of u is just delta. So actually no, this is lambda. So these two notions actually agree. So what this says is, for any set of node potentials, if you replace the cost by the reduced cost, then you get gauge symmetry. In particular, it means that if you run Newton's method on the original instance, initialized with delta naught, the behavior is the same if you run Newton's method with the cost replaced by the reduced cost and the initialization replaced by this. So this is sort of like a gauge symmetry that we will crucially use to argue strongly polynomial convergence. So so with that in hand, let us now try to prove theorem 1. So theorem 1 states that the Newton-Dinkelbach method computes yu high in a strongly polynomial number of iterations. Well, I included an asterisk here because now I sort of cheated by using the look-ahead technique. In fact, this statement also holds if you use the conventional Newton's method. But with the look-ahead, it's easier to illustrate the ideas. So again, we let P1 up to Pk denote the loops that are produced in each iteration by Newton's method. Right. Then again, by gauge symmetry, we can assume that the optimal value is 0. And another bonus that we get is that by shifting the cost, we can also assume that the reduced cost on every edge is non-negative. Then again, we know that with the look-ahead technique, the cost of every loop decreases geometrically. Now, to complete our proof, we will create a layered graph from our original graph. So the construction is as follows. You isolate out the node u, and then you create n-1 layers. Each layer consists of a copy of v minus u. And then between two layers, let's say this is v1 and this is v1. So if they correspond to the same vertices in the original graph, then you add this blue arc with cost 0 and gain 1. And then the edge construction for the remaining edges is as follows. If you have v1, v2 here, and v1 and v2 is in the original graph, then you simply add a corresponding edge connecting the two with the same cost and discount factor. And this completes the construction of the layered graph. And then it is not too hard to show that Newton's method behaves similarly, both on the original graph and the layered graph. Now, why do we construct such a layered graph? It's because of this property that we need called subpath monotonicity. So let us look at two loops which are produced by the Newton's method, Pi and Pj. And suppose that they share a vertex v. Okay? And suppose that I is less than j. So Pj happens after Pi. Then we have the following property that right. So let me just draw the two loops. So let's say this is P of I, and let's say this is P of j, and they share a vertex v. Now, if you look at the UV subpath of the two loops, it turns out that the gain factor of the subpath of the later loop is at least the gain factor of the subpath of the earlier loop. And this is very important for strongly polynomiality. Because now let us look at one particular loop, for example, and we look at an edge whose discounted, whose not discounted cost, but whose cost multiplied by the gain factor of the subpath is at least 1 over n fraction of the cost of the loop. So recall the definition of C of Pi, right? It is the sum of E in Pi, and then there will be a gamma factor in front, which is just the subpath followed by the cost of that path, right? So, so we know there is at least an edge that has at least 1 over n fraction of this. And because we know that the cost of a loop decreases geometrically, after log n iteration, this edge can no longer appear in future loops. Because if it appears, then it occurs with a higher gain factor by subpath monotonicity. And so you get a contradiction. And this is all good because the reduced cost of every edge is non-negative. So there's no cancellation that happens. Yeah, so that's the main idea for arguing strongly polynomial for Newton's method. So the previous proof tells us that within log n iterations, we can eliminate an edge. And in our layered graph, we have mn edges. So it tells us that Newton's method takes mn log n iterations to compute yu high. Same can be said about yu low, it's analogous. Now, if you argue it more carefully, you can bring the bound down to O of mn. And since we have to compute the loop bounds for every node in our graph, this gives us a total of mn square iterations for 2vpi. Now, we will use an idea which was first given by Madani of adding nodes one by one to improve the running time further. So here's the idea. You start with the empty graph, consists of only the singletons. And then in every step, in every phase, we are going to add the edges which are adjacent to U. And then we run Newton's method on this. So you can think of this subgraph as a subsystem of our 2vpi's, of our instance. So we are solving for yu high in a smaller subsystem. And then once we've done that, we repeat the procedure again. We add edges adjacent to another node, and then we compute yv high for this new node v. The benefits of this implementation is that now subpath property holds in the original graph. We don't have to go through the layered graph anymore. So the layered graph blows up the number of edges by a factor of n. Without that, we can actually save a factor of n. So this gives us an overall running time of O of mn. Another benefit of this approach is that when Newton's method terminates, we actually get a feasible solution of the system immediately. Previously, we only get yu high for every node u. So we still have to run some Bellman-Ford subroutine to get a feasible solution. Okay, I'll conclude my talk with some open questions. So every iteration of Newton's method involves running Grapevine, because Grapevine solves the parametric problem h of delta. Grapevine is just Bellman-Ford, so it takes O of mn time. So this gives a total running time of m square n square. So this is still shy of the current state of the art of Hochbaum-Naur, which is mn squared log m. So the question is whether we can make our algorithm competitive with this running time bound. On the lower bound side, is our analysis tight? Can we construct an instance where this implementation of Newton's method does take order of mn iterations? Now, the gauge symmetry idea in this problem has proved to be very useful. So another important question is whether we can apply these ideas to more general problems, such as non-deterministic MDPs or the minimum cost generalized flow problem. On the Newton side, we have accelerated it by looking ahead. But this is only one acceleration scheme. It could very possibly, it is possible that there are better acceleration schemes that are suited for different problems. And then the last question is whether we can apply Newton's method to other fractional combinatorial optimization problems. And that's it from me. Thank you very much for your attention.
Any questions for the speaker, for Cedric? Please feel free to unmute yourself and ask questions. Okay, I have a question. So Cedric, like it seems like you are there issues with like some sort of convergence issues where you approach like the solution like ever so slowly? Like maybe I'm like missing something which is obvious here. Like, are there such kind of issues?
You mean like you get arbitrarily close to delta star, but not quite?
Yeah.
That is a valid question. So the thing is you don't, because each Newton iterate corresponds to some combinatorial structure. Okay. So we are trying to solve the parametric problem. So let's look, exactly. So this line right here,
right.
We are actually maximizing over a set of discrete structures X. So we don't get convergence issues as in the continuous world.
Okay.
Yeah. So there's no need to round off a solution or something.
Okay. Any other questions?
So when you find a sequence of bad iterations and you overshoot, you just go back and walk through all the bad iterations. Is there any sense in just like going backwards?
Yeah, like for example, my estimate was too much. So now I shoot half of that and see whether that's reasonable. Yeah, that could be a plausible acceleration scheme.
I was thinking just even when you overshoot, just start working backwards.
Start working backwards.
Like you go to the left of delta star, you just then move in the opposite direction.
Yes. So what it means to overshoot is that you actually, the h of delta is now negative. Yeah, that's a good point. So maybe for other problems this is useful, but for 2VPI, this is not very helpful because when you overshoot, it might be the case that you actually get a flow generating cycle. So in the fractional combop world, the convex function looks like this, right? it's increasing piecewise, linear, and convex. But in the 2VPI world, it actually takes off after some time. So if you overshoot, then you get a flow generating cycle. Actually, I have to think more about it, but no, that's a valid question, I think.
Any other questions? Okay. So if not, like, then let's thank Cedric again for the talk.
I figured out why. Okay,
Sure.
sorry.
Cedric, you're muted.
Am I muted?
No, we can hear you.
Oh, sorry. You're using.
Yeah, I'm using Edin's tablet. So the thing about overshooting, right? So let me find a page with blank space. So suppose you overshot, right? This is delta star. And let's say you get here. Now, if you start Newton's method from here, then you will get back to the same direction. Yeah. So it sends you back to the right-hand side of delta star. Yeah.
Okay. Yes. No more questions then. So before we end the session today, just an announcement for next week. So we'll be meeting at 1:30 p.m. next week. So we are shifting our seminar time, like the start time, by 30 minutes. We are planning on having shorter talks in general because these are like online talks. We don't really need like the full 2 hours. And next week, Vishnu Narayan from McGill will be talking about fair division of indivisible groups, and where he'll give a very simple proof where like subsidizing like the players with just $1 each can eliminate NB. So it's a very interesting topic. So please do join us for this talk. Right. So that's it. Yeah. Thanks everyone for coming. Yeah.
Thanks, guys.
Sorry, Sharat, so who was the speaker? Because it sounded interesting.
Vishnu Narayan. Let me just quickly text this name on the group. Yeah.
Okay, thank you.
Right, and yeah, it's based on this paper. Yeah. Right.
All right. Yeah.
Okay.
Thank you. And thanks for letting us join the reading group.
You're welcome. Yeah. Thanks for such a great attendance. Yeah. There's a lot of people from LSE. Yeah.
Yeah, we outnumbered you. Although definitely this is submodular because we were, I think, a bit lower numbers than usual. All right.
Okay.
See you.
Yeah.
Thanks, everybody.
Bye.
Yeah.
Bye. So yeah, see you tomorrow or Monday.
Yeah. We'll be joining for the summer school. Yeah.